Okay, so I want to show you a kind of a more interesting theorem. And what we're going to prove is that all prime numbers greater than 2 are odd, right? So first thing I want to do is I just want to show you kind of how you might see this proof in a math textbook. And the proof would be this. It would say, well, let p greater than 2 be a prime. Let p greater than 2, where does that come from? It actually comes from removing the quantifiers, right? So all prime numbers greater than 2 are odd. That's kind of like saying for all p, if p is prime and p is greater than 2, then p is odd. And what we're doing is we're removing the for all, so we're left with some unknown constant. Let's call it p. P is greater than 2 and p is a prime, okay? So this first part actually comes from removing the quantifiers, okay? This is just the result of removing for all p, okay? So then what we need to continue the proof is to say for any 1 less than k less than p, we have that p is not equal to 0 mod k. So let's take a look at this statement. And that's the kind of statement you would see in a math textbook. This actually comes from opening up the definition. And that's one thing that I tell my students. When they come to me and they're trying to do a proof and they say, okay, so I got this far and now I'm stuck. Usually what I ask them is, did you open up the definitions, right? Because more than likely there's one definition in the place that they're stuck that if they simply open it up, then they'll be able to make more progress, right? And the reason that the progress isn't evident is because, well, the things that you need to make progress are hidden under a definition. I want to make a quick aside here. P not equal to 0 mod k. That's kind of the mathematical way of saying that k does not divide p. Okay, and in fact, p not equal to 0 mod k, what's that's really saying is that the remainder of p when divided by k is not 0. Right? So if it has a non-zero remainder, then it's actually not divisible by k. Okay, that's you'll see that expression a lot, and I just want you to kind of understand what it means right now, which is just, sorry, that just means that k does not divide p. Okay, in particular, the proof goes on. P is not equal to 0 mod 2, which means that 2 does not divide p. Right? Well, the reason this is true, of course, is that we just said that it was true for all k between 1 and p. 2 is between 1 and p because p is greater than 2. So that's one of them, right? We said for all k. We can actually remove the quantifier for all k. Okay. Thus p is odd. Actually, that comes from the definition of odd. What does it mean to be even? To be even means that it's divisible by 2. What does it mean to be odd? That is not divisible by 2, which is what this statement here says, right? Not divisible by 2. Okay, so that's how you would see it in a math textbook, and now let's see how you would do it kind of in a formal setting. Okay, so the first thing that we're going to have to do is to translate the English into kind of a more formal syntax, symbolic form. So all prime numbers greater than 2 are odd. For all p, if p is a prime and p is greater than 2, that's the all prime numbers greater than 2, well, that implies that p is odd. Okay. One thing that I do want you to see that's actually pretty important here, look at this for all p. That includes everything between this and that. Okay. So this parenthesis closes here. So notice that it's the same p we're talking about. Is a p that is prime and greater than 2. That p is the one that's odd. Okay. All right. Let's continue. So here's our proof. This is actually the statement that we're trying to prove. We're trying to show that that's equal to true. So let's go to the next step, right? So what have we done? We've removed the for all p by choosing, well, an unknown constant, right? An arbitrary p. So that would be c sub p. If c sub p is prime and c sub p is greater than 2, that should show that c sub p is odd. That should be enough. All right, this looks like a kind of a horrible step, right? But all this is saying, oops, up to here, okay? All that's saying is that C sub p is prime, okay? So we open up the definition and we're replacing equals by equals, which is the kind of thing that I expect us to be able to do, okay? Now that we've done that, then we have again a statement that has quantifiers. So what we're doing is we're moving the quantifier outward, okay? And in particular, notice that there's two parentheses here. Now there's only one parenthesis before the quantifier because we kind of moved it like that, okay? So we took it out of the, you know, it looks like an implication, but actually it isn't because the for all k came all the way out there. So it's actually removing it from an and, not from an implication. Okay, so next step. Now we got to remove it from an implication. It's not this one, okay? This implication here, sorry. This implication here was never an issue because that was inside the for all k. The implication that we're running into is actually this one here, okay? So that's the one that we have to somehow get past. And in that case, the implication really is outside of the or rather, the and is actually inside, the for all is actually inside the implication. So when we pull it out, we do have to reverse it, and so it becomes there exists a k. All right, that's good. There exists a k, so I can remove the quantifiers, and I get to choose what I want the quantifier to be. Now, I chose it to be 2, okay? How come? Right? K became 2. The reason is that I'm thinking of odd C sub p. That means that C sub p is not divisible by 2. And notice that I have here not divisible by k. Now it's not divisible by 2. That seems like a good move. That seems like it's going to get us to the proof. I'm allowed to choose the k, so I might as well choose one that I believe is going to get me there. 1 is less than 2. Well, that's just true, right? So I can just immediately say that. And because I have true and 2 is less than C sub p, well, I can get rid of the true. And so now I just have 2 is less than C sub p. And that should imply all of these things that, that we've seen before. Okay. 2 is less than C sub p is an implication. So not 2 less than C sub p, or, 2 does not divide C sub p. That's what I had. And by the way, C sub p is greater than 2. All that should imply that C sub p is odd. So let's see. Not 2 is less than C sub p and C sub p is greater than 2, or C sub p is not divisible by 2 and C sub p is greater than 2. What have I done? It's just a distributive law, right? So I have an or something, and something else. So just use the distributive law to bring that in. And one of the reasons I did that was because I'm looking at this term here. Not 2 is less than C sub p. Isn't that the same thing as C sub p is greater than 2? So this will simplify quite a bit, right? That seems like a good move. Okay. All right. That's actually where I'm headed. However, I had 2 less than C sub p greater than 2. I'm swapping that so that it's more obvious that this is just a propositional statement. And so now that's false, right? It is not true that 2 is less than C sub p and 2 is less than C sub p. That can't happen. So yeah, that was the simplification that I was hoping for. Okay. So now I have false or something. That's just a something. So what I've managed to show is that either 2 does not divide C sub p and C sub p is greater than 2. That implies that C sub p is odd. All this work is not the quantifiers. All this work is just the normal reasoning that we have to do for predicate logic, right? Isn't that amazing? So let's continue. This is where we're at, okay? 2 does not divide C sub p, and 2 is less than C sub p. That should imply that C sub p is odd. So to do that, again, I have an implication, so let's turn it into not or. So it is not true that 2 does not divide C sub p, I should say, and C sub p is greater than 2. All that, ORed with C sub p is odd. As before, Um, I actually want to use the distributive law here, right? But before I even get there, let me go ahead and change the inside to an or, okay? And I can do that with De Morgan's law, right? Okay, so that means that it is not the case that C sub p is divisible by 2, or C sub, not the case that C sub p is greater than 2, okay? This stuff is actually hard to read. Now that I have a whole bunch of ors, then we're going to use associative law, okay? So we're going to move some things around here, and actually the first thing that I want to try is right here, odd C sub p. I'm going to go ahead and expand that. C sub p is odd if it is not divisible by 2, okay? Which I just want to point out is what we have going on over here. So you can see where the proof is headed. I want to get those two terms together, and they're ORed. This is in its positive form, that's in its negative form. So those two terms should actually be equal to true, and then the proof is done, right? So that's where we're trying to go. All right. So let's rearrange it. In order to be able to get those two terms together, we use the commutative law to get them closer, okay? And now the associative law finally to get them together, okay? And so what are we going to do now? Well, those things are just true, right? Power complement, because they're x or not x. And now I have not, something, or true. Oh, I know what that is. That's just true because of or null. So that's actually the end of the proof, okay? So let's recap for a second. Let's see how this went. The quantifiers really weren't a problem, right? I mean, we took the quantifiers out. We made some good choices for the existential ones. And then there was just a lot of propositional work. This is typical, right? Going forward in this course, as soon as I feel that you really got the propositional work done, then I'm perfectly happy to see you short circuit a lot of the discussion and say, by propositional reasoning, okay? I just know that you know how to do the propositional stuff. So as soon as you can convince me that we've gotten there, then we don't have to do that anymore, right? Because those are just details, right? Those are things that we can do in principle. They're the kind of things that I want a computer to do for me, okay? The other thing that was tricky was kind of knowing what odd was. You needed to know what odd C sub p meant. You needed to know what prime C sub p meant. We actually needed definitions for those, okay? So that's actually one of our problems, because we can do this kind of reasoning for arbitrary predicates like p and q, but it gets tougher when you're talking about specific predicates like odd and even and prime. So that's something that I want you to think about. We need rules for those predicates, right? So all the things that you already know that you've seen before, like for example, you've seen before what it means to be divisible by, right? We don't really have rules that tell us how to reason about those, okay? So part of what we're going to do in subsequent lectures will be to develop those rules so that you can actually reason about things that you learned about when you were in elementary or middle school, okay? But now we're actually going to be able to prove things about those. Back then you were just learning facts, right? This is true, and you believed it because your teacher told you. You're not going to do that anymore. You're actually going to be able to prove things by yourself.